Okay, students. Today I'll go over the Smith chart, and this was a tool developed in 1939 by this person named Smith to allow for microwave circuit engineers to design microwave circuits. And so way back then in 1939, obviously they didn't have computers or really calculators. They had slide rules. And so they needed graphical representations and tools to solve problems. And so Smith realized that this chart, this construction that he made, was quite useful, and it continues to be used today. So really, what it is mapping the reflection coefficient and other values onto the complex plane. And this complex plane is defined with the real part of the reflection coefficient along the real axis and the imaginary part of the reflection coefficient along the imaginary axis, or so the x and y axes. All right. Okay, and so that is the reflection coefficient of the load. Okay, and so it has both a magnitude and phase as well. So you can either express it in terms of real and imaginary components here, or a magnitude and a phase. All right, and so you know how to work with this with either one of these two ways of expressing a complex number. You know how to do that very nicely. You know that a magnitude, for example, will provide you with a certain distance along the real axis, and then the phase portion means that you will then progress around the complex plane, about the origin of this complex plane, by a certain angle theta sub r to get to the point of interest. So A, for example, in terms of real and imaginary parts, can be expressed as this up here. And in terms of magnitude and phase, we get that it has a magnitude of 0.5 and a phase angle, theta sub r, of 53 degrees. All right. Okay. And so that is just the reflection coefficient of the load itself. But the very next step in this construction, I'll do as best as I can with my poor tools I have to work with here, is to find the phase shifted reflection coefficient, which is given by this theta times the amount of phase shift, e to the minus j 2 beta, where d, as you'll recall, is the distance from the load towards the generator. So it's 0 at the load, and therefore gamma d will be equal to gamma at the load, which makes sense. And it changes, gamma d changes from gamma as you go to greater and greater distances away from the load. So as d goes from being 0 to not 0 and some positive number, all right, gamma sub d will be different than gamma, but not its magnitude. Its magnitude will always be just gamma. The only thing that will change is the phase of the quantity, that it will acquire an additional phase of minus 2 beta d, which on the complex plane says that, well, okay, if we know the point A right here, and it has a certain reflection coefficient gamma, as I go towards the load, towards the generator, my gamma will stay the same magnitude, but we will go in a counterclockwise direction because of the minus here. And depending on how far towards the generator we go, we will land somewhere on this circle defined by the point A that was on the periphery of the circle, which represented the reflection coefficient just of the load. So at a certain position, my new reflection coefficient, my phase shifted reflection coefficient would be given by this quantity. All right. Okay. And so we have two things at this point, and only two things at this point. Of the many that the Smith chart will provide, we've illustrated only two. One, that the Smith chart at its deepest level, at its most fundamental level, is simply graphing the reflection coefficient of the load. Okay. However, we can also get the phase shifted reflection coefficient off this chart, the phase shifted reflection coefficient at any distance d away from the load towards the generator. Okay. So those are the first two things we can get with the Smith chart. And again, we'll be going over lots of examples of this, as well as spending Friday's class on this as well. Okay, but let's get more. Let's get more pieces of information from this Smith chart, or let's put on the chart more curves, more constructions, more tools. And so what is something we would like to know from some sort of tool to design microwave circuits? Well, we would like to be able to plot on this tool impedances, the impedance of the load, so the Z sub L, as well as impedance as a function of distance away from the load, Z sub D. So two additional pieces of information. On the next two slides, we will look at Z sub L. All right, first of all, we often and always with Smith charts normalize it relative to the characteristic impedance of the line. All right, so Z naught. So we get this equation right here. For gamma in terms of Z naught, we can invert that to get gamma in terms of ZL. We can invert that to get ZL in terms of gamma, and this is what we get. And then, and remember, this is still just the load impedance, Z sub L. Z sub L in general has a real part normalized relative to Z naught. So it's a resistance, normalized resistance, and an imaginary part, which is the normalized reactance. All right. So we have this equation and this equation. We can combine the two to get this and figure out what R sub L and X sub L are in terms of the reflection coefficient, the components, the real and the imaginary. And we get these two equations that give us R sub L and X sub L in terms of the components of the reflection coefficient, meaning the real and the imaginary parts. From these two equations, we can cast these into this for R sub L equation and this for the X sub L equation. All right. From that, we immediately recognize those two equations are in the form of an equation for a circle. All right. Circles that have different radii and different centers. All right. So let's focus on this one for the moment. We see that my Y naught is 0. So these circles always have at their center along for the Y naught value is always at Y is equal to 0. All right. Whereas for the X positions of its center, it's given by this right here. So these circles are always going to be centered about Y is equal to 0, but at different X values. When RL is 0, it will be centered. When RL is 0, it will be centered at the origin, 0, 0. So we have one circle. So when RL is 0, it will be centered about 0 and 0. That's X naught is 0 and Y naught is 0, and have a radius of 1. Okay, so let's skip ahead and show you this slide. We'll be going back and forth a bit. So my RL is 0 will have a radius of 1. So this right here is 1. And it's centered about this point, the origin of this complex plane, 0, 0. Now, let's go back to the slide. As R becomes progressively larger, so no longer 0, I'm becoming progressively larger, we will still see it's always centered about y is equal to 0. But now the x position changes. As RL goes from 0 to a large value, we get large over large. It should go to being centered around x is equal to 1. X naught is equal to 1. And with the radius, that becomes progressively smaller and smaller. 1 over a large number is small. So as my RL value becomes larger, we should be getting, our circle will shift from being centered about here to being centered about positions that are getting closer to this value of 1 as RL becomes infinitely large. And as well as shifting its center, the radius becomes smaller and smaller. And we see that both of those things happen. So on the Smith chart, we are going to plot a family of curves for different RL values, starting at R sub L being equal to 0 and getting to be progressively higher numbers, always being greater than 0, so always positive values. All right. No passive microwave circuit has a normalized resistance that's less than 0. All right. Okay, so that's our RL family of circles. Remember what RL is. RL is simply the normalized load resistance. All right. Okay, let's put that aside just for a moment and look at the second family of curves. The second family of curves is given by this equation here, and it deals with the normalized reactance. All right, X sub L. Okay, first of all, X sub L can be positive or negative. All right, and that's fine. And we also see that it is very different. First of all, this for the RL family of curves, it was always centered about y naught is equal to 0. Whereas here, my y naught changes depending on what XL is. If XL is very small, say close to 0, then my y naught is very, very large. All right, either positive or negative, depending on the sign of X sub L, whether that's positive or negative. All right. For very large positive XLs, then my family of circles is centered about very large positive y naught values. Okay. But notice that my X sub naught for these family of curves is always 1. All right. And my radius for very small X sub L's, my radius is very large. And for very large X sub L's, my radius is very small. Okay, so let's put those family of curves onto our construction. So there they are, the blue lines. So the blue lines, we said they're circles, and their centers are always at x is equal to 1. X is equal to 1. So my center is always going to be along this line. That's my x naught is equal to 1. Okay. But my y naught value, going back to this, my y naught value changes. All right. Let's look at only positive values for x sub L for the moment. For very small x sub L's, like say 0, then but still positive, we have 1 over a very small number, and so my center to my circle for y naught is way up here, way up here along the this x naught is equal to 1 line. And the radius is very large, all right, for small XL values. So my circle for small XL but positive is going to be way up along this line and have a large radius, all right? And so if we go to the extreme of XL being equal to 0, then my radius goes to infinity. And this point here go all the way up to infinity. And essentially, my XL curve for XL is equal to 0 hugs the real axis. Okay. Now, as we go away from XL being equal to 0 to non-zero numbers, but positive, we see that what happens to the center of my circle and to the radius of the circle is that they both become smaller. All right, so my center will go from very large values and coming down along this line. All the while, the radius becomes smaller and smaller until we start seeing decent portions of the circles that this equation plots out on this curve. So we have XL is 0.5. We can see a decent amount of it of the curve. XL is equal to 1. We can see even more. XL is equal to 2. We can see even more. To the point where XL being very large, if we go back to here, if XL is very, very large, then this goes towards 0, and this goes towards 0. So meaning, but this always remains at 1, meaning that we get to the point where we have basically a half circle as my XL gets to be very, very large. Okay, so we have two family of curves. Curves that represent RL values and curves that represent XL values. All right, and remember again what those are. RL is the resistance, normalized resistance of the load, and XL is the normalized reactance of the load. All right, for a load, they're going to be certain numbers that, and so from what the Smith chart does, it provides you with a connection, something that will associate two things to each other. The RL and XLs with, so the normalized impedance components with the reflection components, gamma sub R and gamma sub I. All right, and so, but we have to put both of those things on the same chart. So, and that's what now the full Smith chart in all its glory does. It puts both of those things on the same chart. The gamma sub R and the gamma sub I are naturally on this chart because that's what defines the X and Y axis in this complex plane, in this construction. But onto this, we now put the family of RL circles and the family of XL circles. We have positive values for XL on the upper plane and negative values for XL on the lower plane. All right. So if we were to zoom in, you can see these different values for R sub L and X sub L. All right, and so for R sub L, we start at 0 for the circle, the largest circle, the circle that has a radius of 1. The circle that has a radius of 1, so this whole big circle has a radius of 1 and centered about the origin of this complex plane. And so that is R sub L is equal to 0. And so then zooming in again, and you have to zoom in a lot because these are such small type. You get RL is 0.1, 0.2, 0.5, 1, 2, and like we had said before, the RL circles, their center converges closer and closer to this point right here with ever decreasing radii values. So R is 2, 3, 10, 50. So that is our resistance from the load. So for a particular load that has a normalized resistance of 1, you will have a certain reflection gamma that is along this line, along that curve. All right. Okay, but that can be any number of different reflection coefficients. All right. So specifying R sub L alone will not uniquely determine the load impedance. All right. You have to define the other aspect, the other component of your impedance, x of L. All right, and so say we have an x of L of, you know, of 0.9. All right, so this is a curve we're working with this example of R sub L being equal to 1. So now we say, well, we know our x of L is equal to 0.9. So then we look at the 0.9 x of L term and we say, okay, well, this is the family of curves on the complex plane that defines XL is equal to 0.9. And so my load has 0.9 reactance, normalized reactance, and 1 normalized resistance, and that point is defined right there. And then from that, we can then find the reflection coefficient. Flip this up, reset itself. Now, the reflection coefficient is that. And so, and then we can read that off by looking at the magnitude of this vector and the phase of this vector within the complex plane. So given a x of L and R sub L, or a Z sub L normalized, we can calculate the reflection of the load. Okay, so those are two additional pieces of information. The plotting on this complex plane of the R sub L and X sub L values, and using going one way or the other, either knowing R sub L and X sub L and wanting to get reflection coefficient, or knowing the reflection coefficient of the load and trying to find R sub L and X sub L. So you can do one way or the other. All right, there's an association between RL, XL, and gamma R, gamma I with the Smith chart. Okay. All right. So far so good. That's the complete Smith chart. All right. Now, but there's other aspects to the Smith chart. Actually, quite a few other aspects of the Smith chart. First of all, we have the sort of the rulers out here, and there's 3 different sets of tick marks for this ruler. The innermost tells you the phase, and really you can start with this is the phase of transmission coefficient in degrees. All right, and you go in obviously 360 degrees, and this chart starts at the phase of 0 right there, right, and then it goes around and it goes in this direction here. So for positive phase angles, you go in the counterclockwise direction in the complex plane. For negative phase angles, you go in the clockwise direction. So this is this innermost graph is the phase angle in degrees. All right, and so that's why if we wanted to go along the line and calculate the phase shifted reflection coefficient, it was with the negative. This was my so. Let me write this over here. Theta d is equal to theta e to the j minus 2 beta d. All right, and this was the theta r, so that that would be our rotation. So as d becomes larger, we go in the clockwise direction in our complex plane because of this minus there. And so say that we had calculated gamma at the load to be this right here. Then if we want to go, then what we do with this is that we then say, okay, that then represents a gamma or a circle that's defined by having its origin at the center and having a magnitude, a radius equal to the magnitude of this reflection coefficient. So this is equal to the magnitude of gamma. All right. Now, so that's just the load. So if we want to now calculate the phase shifted reflection coefficient further down the line, we go a certain angle given by this right here, the theta d. So that tells you the certain distance along the line that we want to calculate this quantity at, and then for the angle, which you need, is what you need to get the information to plot on here. This is the relation. All right, and remember what beta is. Beta is equal to 2 pi over lambda. All right. Okay, and so this is what the outermost set of tick marks represents. The outermost tick marks represent. Okay, and it represents distance along the line, or normalized relative to lambda. So this is d over lambda. All right, and so and then we can start this at any position. So say that by convention we put 0 all the way over here, 0 all the way over here, and then we say, okay, as we go from the load to the generator, we're just going to arbitrarily have 0 here, and then go from 0.1, 0.2, 0.3, 0.01, 0.02, 0.03, 0.04, and so forth. And by the time we get over to here, it is 0.025. And then when we go all the way back, we eventually get 0.49 and finally 0.5. Okay, so what that means is that when we make one complete circle, this is the quantity on, let's call it tau. All right. So as we progress, going all the way around this complex plane, my tau values go from 0 to 0.5. And that represents a d value going from right at the load, d, to a half wavelength away from the load, lambda over 2, because tau itself only goes from 0 to 0.5. Okay. And it doesn't just have to be from the load. It can be from any point. So this we had calculated the impedance of the load in the example we were working with. And then if we wanted to go down the line a little bit and then calculate the reflection coefficient a little bit further down the line, what we would do is, first of all, we would find this value right here, and that's close to 0.158. And then we calculate this value. We determine this value here, and that is 0.208. So this is let's just call it 0.16 is equal to d over lambda. And this point right there is equal to 0.21 d over lambda. All right. And so if we wanted to figure out how far down the line we needed to go, we would subtract these two. We would say, okay, from the load, we have to go a net distance along the line of 0.05 d over lambda. So we have to shift by 0.05 d over lambda. All right. And so if we know lambda, which we're given the frequency, and so therefore, then if we're given the frequency mu, we can determine, and we know the speed of the wave, say it's equal to the speed of light down the transmission line. Then we have this relation there, and so therefore we have lambda is equal to c over the frequency mu, or f. Another way of expressing it. We can calculate lambda, and we can figure out then the necessary d that we have to go away from the load to get to a point where we get the reflection coefficient to be that value. All right. Okay. Complex, it's a mess. A little bit this drawing. I'll do better on Friday when I can write a little bit more clearly on the screen in the classroom, but this is at least a good starting point. All right. So the outermost axis, let's complete that. This is called the wavelength toward generator axis, or set of tick marks. And this tells you how far down the line from the load towards the generator. All right. And it doesn't necessarily have to be from the load. It can be at any starting point along the line. And if you just want to shift towards closer to the generator from that point, you know how various things will change going from here to here. Now, if you want to go a little bit more towards the generator, you go to here, and you go to here, and so forth. All right? Okay. Okay, so again, we'll do lots of examples to try to make this clear as we work through this. Okay. So let's get this back up. Okay. So basically this is the same thing. I've already talked about the outermost scale being wavelengths towards the generator. So it's a certain amount of distance normalized by the wavelength that you want to assess some quantity, reflection coefficient or impedance values. And so that's that outermost scale, and it is the one used the most, right? Okay. So, we now have a variety of different things on this complex plane, on this construction. The impedance, gamma R, gamma I, the normalized, so we have the impedance. Well, first of all, we have, by its very definition, gamma R and gamma I, the components of the reflection coefficient of the load. Then we talked about how to get gamma at any position along the line. That's called the phase shifted gamma. And for that, we go in the clockwise direction, and we apply the gamma sub d is equal to gamma e to the minus j to beta d. All right, and so we can get the phase shifted reflection coefficient at any point along the line. And then we added on the two family of curves, the two family of curves that allow you to calculate or associate with the reflection coefficient, the impedance components, the normalized resistance and the normalized reactance. Okay, now we have the standing wave ratio circles that we can also plot on this curve, on this construction. So if you'll recall, the standing wave ratio is given by 1 plus gamma over 1 minus gamma. All right. So when gamma is a certain magnitude, S as well will be a certain magnitude in this construction. All right. Obviously, they're not equal to each other, but when one has a constant magnitude, which we know that with my x-axis being gamma R, and my y-axis being gamma I, that circles centered about the origin define gammas of constant magnitude. And with S being associated with the magnitude of gamma in this way, they also have circles that are centered about the origin of this complex plane. All right. So, say for example, we have gamma is equal to 1/2. All right. So then we have 1 plus a half is 3/2 over 1 minus a half is equal to 1/2. All right. Or we have a standing wave ratio of 3. All right. So that and that defines a circle of radius 3 and centered about the origin. All right. Okay, and so now what we can do is that we can now also calculate S. So S is numerically here, this right here. S is numerically equal to the value of the resistance of the line. So the real part of the impedance, but along the line at the point where we have a voltage maximum. All right. Okay. So where we have a voltage maximum will be right here, right at this location, right where the circles that define the standing wave ratio intersect the x-axis. All right. We will have a voltage maximum there, and we will only have an effective resistance of the line at that location, and we state that resistance, we define that normalized resistance at that point to be R sub naught. This is the point at which the SWR circle intersects a real gamma axis to the right of the chart's center, so right here. All right. So this gives my R sub naught, and so we can get the standing wave ratio in this case, and it turns out to be 2.6. So this is determined from us going into this, zooming in and saying, okay, what is the R value here? All right, it's greater than 2. It doesn't quite get up to 3. It's 2.24, a little bit more than 2.6. All right, it seems to go a little bit beyond 2.6. That's my R value, and that will be equal to my S value because of the equation in the book that derives this equation. Well, it's a set of equations that we compare the two, and we see that that equation 2.125 is very similar to 2.123. Yeah, actually, 2.125 is very similar to 2.126 in volume in addition 7. And so that allows us to connect this right here, the R that we can read off from our RL family of curves in the Smith chart, and say, okay, that is our standing wave ratio, all right? Which itself gives a connection between the magnitude of the reflection coefficient. So on this Smith chart, we have a lot of information, all right? SWR, voltage maximum, voltage minimum. This is the location of voltage maximum along our line, voltage minimum along our line, reflection coefficient, impedance values, and everything. All right. Okay. We can get some additional piece of information. So besides impedance, we can also get admittance from this Smith chart. So the impedance to admittance transformation is really easy. Basically, we just go in reverse. If we have an impedance that takes us to this point right here in the Smith chart, so this is a certain gamma R and gamma gamma I, gamma R, and gamma I. And then from that, we get an RL and XL value by looking at our family of curves. To then go to the admittance, which, by the way, is given by 1 over the impedance. All right. So Y is equal to 1 over Z. All right. And both of these can be the phase shifted. So D is equal to 1 over Z sub D. All right. But and then we also have Y naught. The characteristic admittance of the line is equal to 1 over Z naught. The characteristic impedance of the line. We again, we normalize relative to Y naught. The normalized value of the admittance has both a real and an imaginary part to it. And what we find is that to get G and B, the conductance, normalized conductance and normalized susceptance, we just simply go 180 degrees. We make a 180-degree phase change, and we read off in the same family of curves. The RL value that we read off from the Smith chart here will give us G, and the XL value that we get at that point will give us B. And so once we know the position A and we get the impedance, we just go down to B, 180 degrees away, and read off the RL and XL values, and those turn out to be G and B. So it's a very easy way to get the admittance as well. So we can get a lot of pieces of information from the Smith chart. I've listed them out several times at this point. All right, so let's do an example. Let's try to go to full screen mode on this. Let's see if I can do that. Read mode, maybe? Yeah. Okay. And that's a fond of that, actually. Let's escape out of here. All right, we'll leave it at that. All right, example 2-11. Okay, so with this, they don't put down all the information that they give, as well as certainly don't even put down here what we're supposed to determine. So let's read off this problem from the book. They do say we have a 50 ohm lossless transmission line of length 3.3 lambda, and it's terminated by a load that has an impedance of 25 ohms for the real part, the resistance, and 50 ohms for the reactance. All right. Now, for part A, what they want is to use the Smith chart to find the voltage reflection coefficient. Fine. And so they want to find, first of all, just a reflection coefficient right at the load. All right. So we can just focus on that for right now. That's A. When we get to B, I'll read what they want from B. All right. So from A, they want the voltage reflection coefficient. And they give you that it is 50 ohms, characteristic impedance of the line, and Z sub L is 25 plus 50J. All right. So first of all, we have to find the normalized impedance of the load is given by this. All right. And then we use the very first equation that, and with that being the impedance of the load, then we have our R is 0.5, and our X sub L is 1. So my RL, we go to the 0.5 curve. We go to the 0.5 curve here, so it's going to be somewhere along here. And then we go to where we have 1 for the XL. And here's 1 for the XL. So we go down, and right there is our reflection coefficient. So that's our reflection coefficient. right there, and then we can we can use our rulers to figure out what the gamma it is at, and then express it in terms of a magnitude. They basically say back before computers and everything, people would actually measure on the piece of paper. They would plot this thing out on a piece of paper, and that's what I'll do, and I'll bring them into class for Friday. They plot this out, and then they measure this distance from here to here, so that distance there, and that will be, and then they will measure this distance to this distance, this right here, and they would then divide through by this distance by this one here. And when they and then you would get in that case 0.62. That this would be O to A is 0.62 of what O to O prime is. All right, and then they would measure the angle above the real axis, and it's 83 degrees. All right, so we have that to be the reflection coefficient. Okay, so part B says to calculate the voltage standing wave ratio. Okay. All right. So with the voltage standing wave ratio, you will then, what you do is that you will create a circle centered about the origin that has O to A as the radius. And so that's this blue circle is that circle. And the standing wave ratio is the R value from the Smith chart when it intersects the real positive real axis. So let's zoom into this point right here. And we see pretty close, it's a little over 4. In fact, it's 4.26 is what R is, and therefore that's what S is, the standing wave ratio. So that's B, S, calculating S. All right. Let's see what C is. See, the distance of the first voltage maximum is the first part of C, and the second thing of C they want is the distance to the first voltage minimum, both from the load. All right, so we have this at the load, and we have this is the position of the first voltage maximum along the line, and so we do what we have said before. We go up to this relevant tick mark, the ruler, and we see that this is right at the load. So we have that number is going to correspond to the load location. Whereas this is the position of our voltage maximum right here, and that's at 0.25 along the load. So the distance we have to go from 0.135 to 0.25 lambda is that subtracted from each other. And so we get 0.115 lambda. So we have to go down the line at 0.115 lambda until we get to, and at that point we will reach a voltage maximum. All right. Okay, and so then the first voltage minimum is right here. All right, and that's at 0.5 lambda. So we have to go from 0.135 lambda to 0.5 lambda, so a difference of 0.365 lambda down the line to get to the first voltage minimum. Okay, so that is parts A, B, and C. D asks for the input impedance of the line. Okay, so so D asks for the input impedance for the line. So that means we go all the way to the end of the very line, all the way down to 3.3 centimeters, or 3.3 lambda down the line, and we find what the characteristic impedance is. And so with that, so to do that, we say, okay, well, 3.3 lambda. First of all, we're going to start here, and we're going to go around here, And when we get back to here, we've gone half a lambda down the line. We go another half a lambda. So we go half a lambda down the line. And we get back to the same position. We get half a lambda again down the line for a total of 1 lambda down the line. And we get back to the same position. And we do that until we get to 3 lambda. And then we're only going down 0.3 lambda down the line to get to our final position right here. So going from here to here, we go down 0.3 lambda beyond what we started with. And so this position is 0.3 plus 0.135, or 0.435 lambda down the line. And then we read off the RL value, the R value at this position, and the X value at that position, and that gives us the impedance of the line, the input impedance of the line. Okay? Again, we'll go over this again on Friday. So that's the input impedance of the line is D. I don't know why they labeled it as. So this is the input impedance of the line. All right. So okay, another example. Okay, this is example 212 in the book, so let's make sure that they give everything. The problem is stated in this way. First of all, they say the problem is similar to the example 2.6, except for now we're going to use the Smith chart. Given that so what they say is that given that the standing wave ratio is 3 on a 50 ohm line, and that the first voltage minimum occurs at 5 centimeters from the load, and that the distance between successive minimum is 20 centimeters, find the load impedance. All right. Okay, so they do give S as 3, they collect the givens. Z naught is 50. First voltage minimum is at 5 centimeters from the load, and the distance between adjacent minimum is 20 centimeters. Well, okay, so first of all, we know that the distance between adjacent minimum of the voltage along the line those are spaced at lambda over 2, period. A periodicity of lambda over 2. And so we know that our wavelength is 40 centimeters. So our wavelength is 40 centimeters. Okay, so that's going to be this 40 is our lambda. Okay, now they give us that the first voltage minimum is at 5 centimeters. So in terms of lambda, 5 centimeters is only 12.5%. So it's so this d min in terms of lambda is 0.125. Okay. All right. So we've gotten that information, and we know that our line is 50 ohms. All right. Now we haven't used this fact yet. The S being equal to 3. Okay. So this S is equal to 3. And we know that we've said before that the S is equal to R somewhere on when it crosses the real axis. So we determine what this R is. This S is equal to 3 right there, and that's what R is at that location. So we know that. That the reflection coefficient is going to be along this curve defined by this standing wave ratio. All right. Okay. So we now have this line right here, this blue line that will connect up all the relevant points in this example. Okay. So now, we say now our voltage minimum always occurs on the real axis, but the negative of the real axis. So right here is our first voltage minimum. But we have to go 5 centimeters down the line to get to that position. And so, so our load is somewhere in this direction. And so when we go this distance from point B to, when we go this distance, we get to the location where the load is, the location on the Smith chart that tells me the impedance of the load. All right. And so we progress backwards in the Smith chart from B, where we know the voltage minimum is, by this amount towards the load. And we get to this point and we read off what R is, and we read off what X is. And that gives us the impedance of the load. So this is the R and this is the X. Since we have a 50 ohm load, we unnormalize that by multiplying by 50, and we get the full impedance of the load. All right, and so that's yet another example. And then we will go back over this a little bit more slowly and carefully and expand it up on the overhead so that we can see all the numbers a little bit better, but this is at least a start to this fairly complex construction called the Smith chart.